Good morning and good afternoon, everyone. My name is Konkahe, and today I will present my topic entitled Application of Derivative and Integral in Real Life. In this presentation, I will explain what calculus is, the differences between derivative and integral, and how these two concepts are used to solve practical problems in our daily life. Before we look at the application, let us first understand what calculus is. Calculus is the branch of mathematics that studies change and accumulation. It is divided into two main parts. The first part is derivative and also called differential calculus. The second part is integral and also called integral calculus. For example, a derivative measures the rate of change of a quantity and also finding the maximum volume of a box or a minimum production cost. On the other hand, an integral measures the total accumulation of a quantity. Instead of looking at how something changed at one moment, integration adds up many small changes over time. It is represented by the integral symbol. For example, if we know the velocity of a car, integration allows us to calculate the total distance traveled. It can also calculate the total amount of water consumed over a period of time. The objective of this presentation is to explain the basic concept of derivative and integral in calculus, to identify how derivative and integral are applied in real-life situations, and to demonstrate how calculus help over practical problems in fields such as physics, engineering, and business. Before going into detail, here is the quick overview for today's video. Derivative and integration can be applied in different real-life applications due to its different formula and concept. The first example for derivative in real-life application is driving a car, which is calculate the rate of change of velocity. The position is changed over time and derivative can calculate the car velocity, so it's allowed the engineer use it to design speedometer and braking system. The second example is find the mean and maximum value of the box. By determining the dimension that produce largest possible while using same amount of materials, it can help the product designer to avoid the waste of material. Next, for the integral in real-life application, the first example is distance travel. A car's speed changes throughout a journey. Integral add up all the small distance to find the total distance traveled, and it is useful in transportation system. The second example for integral is water consumption. It can calculate the total consumption of water tank. If water flow into tank at different rates, integral can calculate the total amount of water collected. It can help the company to generate a monthly water bill. For population study, the derivative is used to measure how fast the population changes as the time passes. Instead of only knowing the total number of people in the city, we can use derivative to find out whether the population is growing or decreasing, and how quickly this change happens. If the derivative value is positive, it means the population is increasing, because more people are being added to the area through birth or migration. If the derivative value is negative, it means the population is decreasing, because the number of people living or dead is greater than the number of new people. If the derivative value is zero, it means the population remains constant, where there is no significant change over time. Therefore, derivative help us understand population trends by showing the speed and direction of population changes. Other than that, in geometry, integration is commonly used to calculate the total area under a curve. This is especially useful when the shape is irregular and cannot be measured easily using a simple formula, such as length multiplied by width. The idea behind integration is to divide a large area into many smaller sections. The area of each smaller section is calculated, and then all these small areas are added together to obtain the total area. Therefore, integration allows us to measure complex area accurately by combining many small parts into one complete measurement. Our first application is the rate of change of a car. Suppose the position of a car is represented by st. When we differentiate the position with respect to time, we obtain the velocity bt equal to ds over dt. If we differentiate the velocity again, we obtain the acceleration at equal to dv over dt, which is equal to secondary derivative of ds over dt. So the relationship is displacement can differentiate become velocity, and velocity differentiate become acceleration. The important idea here is that derivative measure how quickly one quantity change into another. For example, if the position of a car change rapidly, then its velocity is high. If the velocity change rapidly, then the acceleration is large. This concept is used every day in transportation. Now let's see how this is applied in real life. One example is GPS navigation system. GPS continuously record the position of a vehicle. By calculating how the position change with time, derivative determine the vehicle's current speed. With this information, GPS can estimate current speed, estimate arrival time, and travel progress. This allows the driver to receive more accurate navigation and better route planning. Another example is vehicle safety system. Modern cars use velocity information in systems such as anti-lock braking system (ABS), adaptive cruise control, collision avoidance system, because derivatives provide accurate speed information. This safety system can react quickly and help reduce accidents. Therefore, the derivative improve both navigation and passenger safety. The second application is finding the maximum volume of a box. Imagine a company wants to produce an open-top box using a cardboard measuring 30 cm by 20 cm. The company wants the box to hold as many products as possible while using the same amount of material. This is an optimization problem. First, we can draw a card box and write the volume as a function Vx. Next, we find the first derivative and let V'x equal to 0. This identifies the critical point. Then we use the second derivative to determine whether the point is maximum or minimum. If the second derivative is negative, then the volume is at maximum. By doing this, company can design boxes that use materials efficiently while maximizing storage capacity. And let's see how optimization is applied in real-life application. For example, engineers use derivative to design routes with a shortest distance and lowest construction cost. This helps save time, money, and resources. Derivatives are also used in designing car braking systems, airplanes, and roller coasters. Engineering use optimization to improve safety while reducing unnecessary stress on the structure. Therefore, derivatives are very important in engineering design. Besides that, derivative can also be used to study population change. Population is a city does not remain constant. It changes continuously because of factors such as birth, death, and migration. However, knowing only the population size is not enough. For example, city planner may ask, how quickly is the population increasing? This is a question about the rate of change, which is exactly what derivative measure. Suppose the population of the city is represented by the function pt equal to 1000 exponential 0.05 times t, where pt represents the population after t years. To find how fast the population is growing, we can take derivative p prime t equal to 50 exponential 0.05 times t. The derivative gives the population growth rate at a specific time. For example, if the growth rate becomes higher in the future, the government can predict that more hospitals, schools, and housing will be needed in the future. Therefore, derivative can help decision makers prepare for future changes. This allows the derivative are not only used in physics and engineering, but also in areas such as biology, healthcare, and urban planning. Now let us look at how derivatives are applied in real-life situations through a population growth. In real life, the population of a city is constantly changing because of factors such as birth, death, and migration. However, knowing only the total population does not tell us how quickly the population is changing. This is where derivatives become useful. By finding the derivative of a population function, we can determine the population growth rate, which shows how many people are being added or reduced over a certain period of time. For example, if the derivative shows that a city's population is increasing at a rate of 500 people per year, this information can help the government predict future population needs. With this prediction, authorities can help and prepare important facilities such as new housing area, school, hospital, and transportation system to support the growing population. Therefore, derivative plays an important role in urban planning because they allow decision makers to understand population trend and make better plans for the future. Now let us move to integral. Our first example is finding distance from velocity. Unlike derivative, integration add together many small changes. Suppose a car has velocity Vt equal to 40. We want to know the total distance traveled during the first 3 seconds. Instead of multiplying velocity by time, we integrate the velocity function. The formula is distance equal to VT integration. Substituting the velocity into the function, then we can get 2t squared. Finally, substitute t equal to 3, we can get 18 meters. Integration allows us to calculate the total distance even when the speed changes continuously. This application can be used in many industries. For example, in aviation, aircraft speed changing during takeoff, cruising, and landing. Engineers integrate velocity over time to calculate the total distance flown. This information helps with flight monitoring, fuel management, and air traffic control. Another example is the railway industry. Since trains constantly change speed because of station and signal, integration helps operators calculate total travel distance. This improves timetable planning, energy analysis, and railway safety. The second application of integration in real life is water consumption. Suppose a factory uses water at a changing rate given by RT equal to 100 plus 20T, and T is represent the time. We want to calculate how much water is consumed during the first 5 hours. Because the rate changes continuously, simple multiplication is not accurate. Instead, we can integrate the rate. Then we can substitute the equation into the integration formula. Then we can get a formula and substitute T equal to 5, and we can get 750 liters. This example shows how integration calculates the total amount when the rate changes over time. And here is a real-life situation. The amount of water used in house, factory, or city changes throughout the day. People use more water in the morning for cooking, showering, and cleaning, while less water is used at night. Because the flow rate keeps changing, it is difficult to calculate the total water usage directly. Integration solves this problem by adding up all small amounts of water used throughout the day. Therefore, water companies also use integration together with water meter data to calculate customer monthly water usage. This allows them to produce accurate and fair water bills. In addition, government use this information to estimate community water demand, prevent shortage, and plan future water resources. Therefore, integration plays an important role in water management and resource planning. Now, let us look to another application of integration. Integration is commonly used to calculate area, especially when the shape is irregular. For example, imagine engineers want to construct a building or highway on a piece of land. If the land is a simple rectangle, we can easily calculate the area by using the length multiplied by width. However, many real pieces of land do not have a straight boundaries. They may contain curve, slope, and uneven shape. In this situation, integration provides a solution. The basic idea of integration is adding many small pieces together to obtain a total amount. For example, in mathematically, the area can be calculated by using the below area formula. For example, if the boundary of the land is represented by the below equation, between x equals 0 and x equals 4, we can use the integration to find the total area. After the integration, the area is 64 over 3, or approximately 21.33 square unit. In real life, engineers use this method to estimate construction area, calculate material requirement, and determine project costs. Therefore, integration helps solve problems where traditional measurement methods are not accurate. Next, let us see how application of integration in calculating land area in real life. In real life, many areas such as farm, forest, and construction site, they do not have a perfect rectangular or circular shape. Because of their irregular boundary, using simple formula like length multiplied by width, they may not provide an accurate measurement. Integration solves this problem by allowing us to calculate the exact area of irregular shape. The boundary of the land can be represented as a curve. And integration divides the area into many small sections. By adding all these areas together, we can obtain the total area of the land. For example, farmers can use the integration to measure the exact size of uneven farmland. Knowing the accurate land area helps them to estimate the amount of seed, fertilizer, and water needed for planting. Similarly, engineers and environmental scientists can use the integration to measure construction area, forests, or lake more accurately. Therefore, integration helps different industries make better decisions by providing accurate measurement of area. that cannot easily calculating by using a traditional method. To conclude, derivative and integration are two important parts for calculus. Derivative measure the rate of change and are widely used to calculate velocity, acceleration, and solve optimization problems such as finding the maximum volume of a box. And also, integration measure total accumulation and are used to calculate distance from velocity and also total water consumption over time. This application demonstrates that calculus is not only a mathematical theory, but also a practical tool used in engineering, transportation, business, and resource management. Therefore, calculus is essential in solving real-world problems and improving efficiency in our daily life.